Welcome back to another exciting episode on Black Body Engineering, where we break down complex digital systems into circuits you can actually build. Today, we're going to be wiring out the brainstem of our 32-bit CPU, the program counter. This is the part that tells your processor what to do next, and remember, without the program counter, your CPU has no direction, is unable to fetch any instruction, is unable to decode any data, and is unable to execute any word. By the end of this video, you will be able not only understand how it works, but you will be able to build it and run it yourself. So let's go ahead and let's make your CPU smarter, one clock cycle at a time. So by now you might be wondering what is a program counter? Well, a program counter is just a special register. In our case, we're gonna build it of the flip-flops that store the memory address of the instruction currently being executed. After each instruction, it usually increases by 4 bytes to fetch the next one, because every MIPS instruction is 30 bits long or 4 bytes. For example, let's say we have our program counter right here, and our program counter is going to be 32 bits long because the address, it needs to be updated. The output is going to go to our instruction register because this is where our program and data is loaded. And part is going to go to a full adder where it's going to be added with 4 bytes. This is the address, and the address is going to be added back to my program counter. So it's address plus 4, and that's going to be fed into the program counter again. In the fed cycle, the PC or the program counter tells the instruction memory what address to read. Then it updates itself for the next instruction. This process is very simple, but it's very important. Without the program counter, your CPU wouldn't know where to go next. So before we go dive in and start wiring stuff, we can build our own program counter, and we're gonna break it down to its core, a deep flip-flop register. Understanding this concept helps you understand what is a program counter really is. Basically, it's just a collection of flip-flops that store the current address. So let's first write a simple. We're gonna do a 4-bit counter, a program counter. So to do that, we have to define a deep flip-flop. We're gonna have a clock, and we're gonna have a reset because we want the program to reset back. And we're gonna have another D flip-flop here, another here, and another here. So D and Q, D and Q, D and Q. I'll have the clock here. So we can have an enable too. We'll have an enable signal here. Let's put it right here. They'll all share the same clock. All of them need to be clocked at the same time. And then our clocks, our D flip-flop, all of them are separate signals. That is our input for our register. and this is going to be our output. And if we want to have a reset input so we can reset. And this is going to be our Q3, Q2, Q1, and Q0. And this is going to be our input for all 3, all 2, all 1, all 0. So if you think about it, the enable signal will activate the register so it can obtain the new data, or our clock signal is being provided to all of the flip-flops, and we have an enable switch so we can serialize all of them at the same time. So this is basically our program counter, and when we actually gonna build ours, it's gonna be 32 of this. Remember, this is 3, 2, 1, 0. So we need to go from 0 to 31, and that is equal to 32 flip-flops, which is a lot. It's 32 bits, so we're gonna have 4 bytes of data that we have to work. So now that we have explained all the theory behind the program counter, we can go ahead and build our own. For the purpose of this one, we're gonna build one with 4 bits, and then we're gonna expand it to the full 32 bits. Logisim already has a counter that we can use, or we can use the register, and we'll define that to define all 32 bits. But for the purpose of explaining, we're just gonna do 4 bits for the sake of proof of concept. So we have 4 outputs. We have 4 outputs here. We can wire all that to a splitter. We're gonna do 4, 4. We have center. We're gonna face it north. All of that is gonna go to our output, which is gonna be 4 bits. We need this too. And we have is face down. And that is gonna be our input. We're gonna have our resource signal. All of that can be wired together. Doesn't matter because we want all of them to reset at the same time. And then we're gonna have our clock signal as well. Because we want all of them to be clocked at the same time as well. We're gonna leave the set floating, but in reality, it should be tied to ground to prevent signals. And if we start clocking the system, you can see like there's nothing getting loaded. But if we set 1, then stores it here. Let's add a enable signal here. So we can do very simple. We just put an AND gate. We clock to the AND gate, and we added an enable signal here. So what's going to happen with this is, as you can see, we can clock the system, but it's not going through. So even if I remove the value from my input, it stays 1. And if I want to do all ones, it won't load into the register until I enable the signal. And I disable the signal, and it holds the value, even if I remove the input. So once we have this, if we try to model the program counter that it adds by 4, what we can do is that we add a full adder. We can add it right here. And the 4 bits. Oh, I put it on the wrong place. So right here, and that is 4 bits. And then we can add a number 4. We can add a constant to do that. So can we do a constant? Yes, we can do a constant. It's 4 bits. And we can add 4. And then this is going to get added back to my program counter. I'll remove this. And remember, it's 4 bits, so it goes from 0 to 15. So let's see what happens. If I activate this, then it goes 4, 8, 12, and then back to 0, because 12 plus 4 is 16. And we don't have 16 in binary, and that is 0. If we change this to 2, and we serialize it, we can see 2, 4, 6, 8, 10, 12, 14, 16. So the good thing about adding this enables this reset signal is that, remember when we were building the instruction register, we were unable to implement the full instruction register of 4 gigabytes. We were limited to 128 megabytes. And we want our pin 27 that is going to come from our instruction register to reset our program counter if it's needed. This gives us more flexibility for automatic and manual control. So now that we have implemented a 4-bit, we can go ahead, and now that we have implemented our 4-bit register, we can go ahead and implement the full register. So the way I'm gonna do it is, I'm gonna use this one that is already a register. I'm gonna extend that to 32 bits. And basically, I'm gonna do the same thing. This is gonna be my clock signal. The good thing about this register is that you can see there's a write enable already implemented there. So I don't have to put an AND gate to gate my clock. So now that I have that, I can use the clock, add it here. I can use the output. This is my output, and that's going to be 32 bits. I can have actually an input, but it's going to be a full adder. One is going to go back to my signal. I'm going to have a write enable signal here. I'm going to have a constant here, and that's going to be 32 bits. And I'm also going to have the reset. I wonder what is this error popping. I want to add 4. Let's zeroize it. And as you can see, it's going to go by 4, 12, 10, 14, 18, 20, 24. So it's adding plus 4. We can also add an output so we can see the output in binary. And you can see how it's going through all the numbers. Or you know what? Maybe I can put it on unsigned. So you can see 36, 40, 44, 48, 52. So it's adding up. If I increase the frequency, it's going to go faster. And that was only at 1024 kilohertz. And if I increase to 248 kilohertz, it goes even faster. And as soon as I disable the write enable, you have the clock that is trying to operate the flip-flop, but the program counter is stuck. It's not going through. And if for some reason there's an instruction that requires me to go back to address 0, it will send a signal here and it will zeroize it. So this is the full 32-bit program counter. Thank you for building with me on Blackbody Engineering. If you're enjoying the MIPS CPU series, hit that like button, subscribe, and drop a comment when you build progress on question.